This is group 17 presenting a multi-head self-attention and spec augment approach for reliable audio deepfake attribution and model recognition. So we've seen deepfakes everywhere in entertainment now, but there's a darker side. Audio deepfakes are getting so good that they're being used for identity fraud, impersonation, scams, and financial fraud, often leading to misinformation due to perfect mimicry of someone's voice. So the real issue we're looking at isn't just that whether the audio was fake or real, but rather we need to identify the sources. So which specific generative model was used for this fake audio in order to trace back where it came from. So what we're trying to do is not only identify whether it's fake or real, but be able to track back to the generating model. So previous work on this is the Lava framework, which has two different levels. They have a first level that identifies the data set that was used. And the second one is identifies from specifically the codec fake data set, which specific model between F01 to F06 was used for generating that audio. Before that, we can see that there's an autoencoder that's trained and frozen, and then later on used in the detection model and the attribution model and the model recognition model. So what we identified as a bottleneck for this is that the error is propagated. So in case the first level misidentifies the data set, then the second level has no chance of identifying the model that was used in the codec fake data set. So what we are proposing is a reimplementation of that Lava framework, but with a bit of improvements. So first, we're going to use three data sets: codec fake, ASV spoof 2021, and the fake or real data set. So the first task, or the first level, the attribution task, will require all three data sets, and each data set is assigned a different class. Then for the second level, we'll have the codec fake data set that will now be used to identify which model or which specific model was used between F01 to F06. So we are using all these data sets are in form of waveforms that we can convert to spectrograms for processing. Our proposed methodology, apart from re-implementing the baseline, we intend on improving the performance of the model or the design of the model by using a multi-head self-attention. So previously in the existing framework, they used a single head attention, which was just basically a convolution layer, but we intend to use a multi-head attention layer. Then we intend to use spec augmentation in order to ensure that the model learns features that are invariant to channel noise or recording quality. And finally, in order to ensure that since the data is imbalance, has a high imbalance, we're going to use the macro F1, which treats every model class with equal weight and ensures that the results we get are accurate. So this is what we managed to do. We can see that the baseline results, the multi-head attention results, and the spec augment with multi-head attention. And based off this, we can see that most of the high performing for at least the attribution model, the detection attribution model, was on the spec augment with multi-head attention. And as you can see, apart from the recall on codec fake, all the other scores were towards the spec augment experiment. And we can see also in terms of the macro F1 score, all the high scores were under the spec augment with MHA experiment. Then for the detection and model recognition, there was a distribution between the multi-head attention and the spec augment with MHA. So the spec augment with MHA overall, apart from the conflicting precision and recall, we have the overall accuracy macro average and weighted average performing better than all the other experiments. So we had a challenge with the scale of the data. We had 102 GB of data, but due to limitations in computation, we had to use a subset of the data. Then introducing multi-head attention and spec augment ensured that we ensured that we had a better model recognition accuracy.